So that convolution is going to be, let's see, I need to do out some, like, let me do out the product of this thing. So let's see, I got all these 1/2 i's, so that's 1/4. I can take out a 1/2 I out of here, a 1/2 out of there, it's 1/4 I squared in the denominator, so that makes it negative 1/4. And let's see, I got a whole bunch of products here. I've got this one. In fact, how many products do I have? 4. Yep. So then I've got this one. And this one is z. This is omega minus z. And then I've got the 500 ones. And 100 z delta. And this one is the minus 250, minus 250, plus 250, plus 250. Okay, did I get all the
2b plus.
So let's see here. I should have one of each. Oh, I see what you're saying. This is a plus, this is the opposite sign, shouldn't it be? And that's this one, right? Minus 500 with the plus 250s, that's this one. And the other one that should come out with another opposite sign is this one, the 500. Okay, cool. All right, so now all of these delta function convolutions are pretty easy to work out. See, this one here, I'm going to put in the z as 500. So this is minus 1/4 delta of minus 250, omega minus 500. That's this first one, plus 1/4 delta of 250 evaluated at omega minus negative 500. The next one is plus 1/4 delta of negative 250 evaluated at omega minus 500. 250 at omega minus 500. Did I do that right? I have a feeling I did one of these wrong. Yeah, I did one of them. This one here should have plus. Okay. Yeah. Okay, cool. All right, so let's see here. But these deltas of 250s, well, let me change variables on them. This is what? This is going to be, where is this one? This one here has its support. It's spiky when omega plus 500 is equal to negative 250. So what's omega? Yeah, negative 750. All right, and what about this one? This one here has its support when omega plus 500 is equal to 250. Where is its support? Negative 250. Yep. And over here, let's see, plus 1/4. And where's this one's got its support? It is, let's see, it's when, yeah, it's 250. And this one here, by process of elimination, is going to be plus 750. Got it. And if you look at it, hey, wait a minute, that's exactly where that trig identity said that they ought to be. So convolution actually recovers that trig identity for you. Now, not saying this is an easier way to do it by any means, but it certainly works. It's at least self-consistent. So what does this mean? Well, this means if I take two tones, and I multiply them together, your ear will hear musically two tones. But those two tones that you had there, one of them is going to be the sum and one of them is going to be the difference. 500 plus 250 is 750. So hear that higher frequency tone. And you'll also have the difference. 500 minus 250 is 250. So you'll hear that as well. So this is used in radios because what you'll do is you'll have the signal you're actually interested in, way out here high in radio frequency land, megahertz. You'll have another frequency that you use to tune the radio. It's a local oscillator that will set that frequency. And what it'll do, this makes amplitude modulation work, is that you will tune this frequency so it matches up with the center frequency there. Well, the sum will be way off at even higher frequencies, but what's the difference going to be? Kind of close to 0. In particular, it means they'll be in the audio range. So this is how radios operate. They take and multiply these signals together to move the signals around. So now, yes, as advertised, let's hear it. So I'm going to load up the code. Hold on a minute here. Okay, so here, first of all, what I'll do is I'll play. In fact, I think I've got one of these already. I do. Okay, so this is a 500 hertz tone. So this is the green guy, the G. Oh, that's not right. That's not right. Okay. So that's this guy. Now let's do the 1000 hertz guy. Okay. And now let's do both of them together. Yeah, right, 10th right phone.
Does this have anything to like beat frequencies?
Kind of. It's like sort of different from beat frequencies. Beat frequencies come from sums.
Yeah.
These are products.
Okay.
Right. So did you? Let's ask musically. Did you hear? Here's the 500 hertz. So the G. Here's F. And then here is F times G. So the pair. Do you hear the two? There are two tones there. One that's distinctly higher, and one that's distinctly like the original, like this one. But it's this dual tone that's present there. Yeah. It's both of those two tones at once. So the point of the matter is that when you're building radio systems, what you'll often do is you'll often isolate and get rid of one or the other of these guys. That way you can control the position of that other one without messing with things. In fact, actually, if you build a radio that does this mixing operation, as electrical engineers call it, taking products of two functions called mixing, what ends up happening is you end up with a lot of stuff that's at much higher frequencies and some that's at lower frequencies. If you do not filter them out, you can get in trouble with the FCC, actually. Mm-hmm. And the way they actually build these things is actually kind of neat. Way back in the bad old days, they did this sort of seat of pants. Now it's much more systematic. But something kind of surprising actually works, and it's like quick and dirty. We don't actually have the ability very easily to multiply functions directly. We can if you really sit down and do it, but it's very expensive. So it's much better to do it cheaply. And the way they do it cheaply is actually this way. It's very easy to add functions. Adding functions is something that you can build with an operational amplifier, for instance. So I could do F plus G. That's no problem. But that, of course, is beat frequencies. That's not going to do convolution in frequency. So what they do is they do something crazy. They say, well, there's a device called a diode. You know what a diode does? No, not really. It can be used. A transistor can amplify. What does a diode do?
It increases the frequency.
What's that?
Does it change the frequency?
It does, but that's not its primary focus. Its primary purpose is something else. Look at the symbol.
One way.
Yeah, it's a one-way valve. Electricity flows very well this way and not very well this way. And in fact, if you plot, this is voltage and the amount of current, it looks something like, looks like this. Looks like this. So if you put negative voltage on it, it doesn't let a whole heck of a lot of current through. That's a little bit. It's called leakage current. But if you put even just a little bit of voltage, you get a lot of current. Sort of like a one-way valve. Turns out this is an exponential curve shifted down a little bit. So it's like, this is like an e to the x minus 1 kind of curve. So what they do is they say, well, diodes are easy to make. You know how to make a diode? There's two good ways to make them. All right. Basically, you take a layer of silicon, and then you take another layer of silicon, and you put either positive or negative charges into each of them. different amounts. So you put into the bottom layer either a lot of positive charges, and in the top layer a lot of negative charges or vice versa. This ends up building up, makes it very easy for electrons which are negatively charged to go one way, as in it's very easy for them to go from the negatively charged area to the positively charged area, sort of easy to get away from all your friends because they repel, but it's very hard to go the other way. It's very hard to take all these, so if you have over here, there's lots of negatives over here, lots of positives over here. It's very easy to take the electrons and make them go this way. Not so easy to make them go backwards. They don't want to go backwards because there's a lot of electrons already there. So what you do is, from a mathematical standpoint, what you do is just do this. You compute this guy. Now why would that help? Yeah, e to the f times e to the g. That's what you get. So in fact you do product the functions. Now you product the exponential versions of these functions, but you make f and g kind of small, so the linearization is about right here. So you end up with a linear approximation of f, a linear approximation of g, or at least slightly distorted versions, and you in fact do product them together nicely. So that's how people build these multipliers. They call them mixers. So anyway, that's a very practical application of this. Of course, in my case I didn't do that. In my case I did it in MATLAB. But MATLAB is cool that way. But that leads us to our next point, and the next part of today's lecture. Because if you remember, I said it's about convolutions, and it's about discretization. Because of course, I can't do any of this wonderful processing. That's analog. But I can't do any of this wonderful processing on my computer, which is digital, without getting the signals, which are analog, into the digital, and vice versa. So I want to tell you how that is done. And there's a very, very famous theorem about conversion between analog and digital. And it goes under the name of the Shannon-Nyquist theorem. There are probably lots of other people who need to be appropriately credited. I don't know who they are. Shannon worked at AT&T Bell Labs, and Nyquist, I believe, was a mathematician, but I'm not entirely sure. They discovered this property independently, but they said if f is a function whose Fourier transform f hat is compactly supported. And in fact, they give this a special name. They say f is band limited. Then it is possible to recover f from discrete measurements. So let's drill down into this. This is a very imprecise statement. Let me be a little more precise about it. So if f hat of omega is equal to 0 when the magnitude of omega is greater than b. That b is called the bandwidth of f. Then you must sample, then samples of f, by which I mean finding values of f and taking a look at them, spaced closer than 1/2b suffice to recover f. Okay, so I want to show you essentially two similar arguments of how this works and why this works. Incidentally, if you look at this, instead of thinking of it as a time there, a spacing, think of the sampling frequency. Must be greater than Turns out than or equal to, but I'll just write greater than 2b. So what this means is, for instance, if you know what human hearing is, anyone know about what the human hearing range is? No, not in decibels, in frequency.
Isn't it like 10,000 to like 80,000 or something?
You got way better hearing than I do. No. It's about 20 hertz up to about 20 kilohertz at absolute maximum. So human hearing is about, goes up to absolute maximum about 20 kilohertz. So if I sample a signal, sample some music at least twice the 20 kilohertz, say 40 kilohertz, then there is no way that you will be able to tell the auditory difference. I mean, unless there are various other nonlinear effects, but just straight from recovering the signal. So what this is saying that if you could sample a signal, a musical signal, at 40 kilohertz, that's as good as you ever will need. Incidentally, 44 kilohertz, 44.01 kilohertz happens to be what the compact disc standard uses as its sampling rate for specifically that reason. And on our projects, we've been working with sampling rates in the order of what? What do we use thus far? The various people have used different ones. What sampling rates have you used thus far? You were synthesizing 8,000. 8,000. So what's the lowest, or what's the largest bandwidth function you can hear with 8,000 hertz sampling rate? Half of that, right? 4,000. So you can hear up to 4,000. Is that anywhere near the top of our range? No. So you can hear defects in the sound. Turns out 8,000 hertz is what the telephone system at one point used. It's enough to recover human speech, but not a whole heck of a lot. Good for music. This is why the music on hold sounds so bad.
Among other reasons.
Among other things. I never mind the musical aspects of it, just the audio aspects of it. This is one of the reasons why it sounds bad. All right, so let's have a look at these theorems. In order to look at these theorems, we need one special technical tool. The technical tool we need is the Fourier transform of a train of impulses. What's the Fourier transform of a sequence of delta functions? Okay, because that will be how we sample. So we'll sample by how? By saying taking f, and we will multiply it, f of x, times a sum of delta functions at our sampling spacing being 1 over 2b, so at n over 2b, and plus infinity. And of course this is. So we'll sample that way. This is how you can sample. That, what is this thing going to be equal to? It's going to be equal to, I mean, in fact, it's on the nose equal to, the sum of f n over 2b delta n over 2b x. Because in fact, because we're multiplying by a delta function, we don't ever need to know what the value of f is, away from where those delta functions are supported. So this is the sampled version of f. So in order to do this, we'll want to do this in the frequency domain, and we'll see why the band limit is important. But look at this, we need to have the Fourier transform of this. Of course, we'll assume we've got the Fourier transform of this and that it is band limited. So we need to find the Fourier transform of this guy. Okay, that's not too bad. So let's find the Fourier transform. This train of impulses. Let's find that. Well, all right, here we go. So that's the Fourier transform of it, so let's compute it. e to the minus 2 pi I omega x dx. Now there's something pretty fabulous about this because they're all delta functions. Okay? Let's make the bold assumption that I can switch the sum of the integral, as one often does when I was a applied mathematician. And then I'm just integrating these complex exponentials against delta functions. N over 2b. That's parameter is x minus 2 pi I omega x dx. Okay. So what do I get? I evaluate this guy by putting x, putting 2n over b for x, e to the minus 2 pi I omega n over 2b. All right? Now if you stare at this, you say, well, wait a minute here. I've seen this before. Fourier, not transform. Fourier series. This is a delta sequence for the Fourier series that came up already. This guy here, this is a delta sequence. In particular, it's periodic. It has a period. What's its period? Well, its period is, it's periodic. And its period is, its period is whenever 2 pi I is equal to minus 2 pi I omega n over 2b. So let's cross all that stuff out, and it's whenever omega is equal to 2b over n. Wait. And the smallest such of these, they all get bigger and bigger. The smallest such of these is when n is equal to 1. So that's the period. So this thing, this Fourier transform of this thing here, let's say, and the spacing between these guys is n over 2b. What is it? It's another sequence. It's a periodic sequence of delta functions, delta distribution, rather. But the spacing is now 2b. Way cool. Now, why is this important? Well, let's see here. We want to know what our function is doing when we convolve the Fourier transform of f with the Fourier transform of this. Now we know what the Fourier transform of this is this delta sequence of delta functions. That looks awfully like that looks mysterious. That's supposed to be 2b. Right. So the Fourier transform of the sampled f, so that's the f times this guy, n over 2b. That Fourier transform of that thing is equal to the product, product, this is the product here, it's equal to the convolution of involved with that delta sequence. That sequence of delta functions. And that delta sequence is spaced like this. No, over n. No. Yeah, it's this. All right. Okay. So the benefit of all this is now this wonderful graphical argument, which mathematicians don't seem to like this so much. I'm a mathematician who likes it. I was shown this by an engineer. I think it's pretty cool. So here we go. Here's my omega axis. Here's f. Now f has a band limit. So let me draw f. And its band limit is that it lives between minus omega and omega. So this is f. That's what f is. It's in there. I don't need to say f here. Okay, now what did I know these delta functions are? They're all spaced by 2b. Whatever. Sheesh. Minus b to b. Okay. So they're all spaced by 2b. And actually, the way I've written it is slightly off. It doesn't really matter a whole heck of a lot, actually. This distance is 2b. So what's the convolution? Convolution well, what does convolving with one of these delta functions do? Shifts that support. Okay? Convolution with another one shifts that support. By how much? 2b. There's some multiple of 2b. Do any of the shifted supports overlap? No, none of the shifted supports overlap. None of the shifted supports overlap. So this is the convolution. So what this means, this is the Fourier transform of the sampled data. This is the Fourier transform of the sampled data. None of these things overlap. So have I lost any information? No, I haven't lost any information at all. So in fact what this means is that right from here I can say I haven't lost any information, but I've thrown away all this information. This is a Fourier transform of this thing. And you say, well, wait a minute. All right, I'm taking a Fourier transform of a delta, but a sum of delta functions. Why don't I just get out delta functions? Why are they spread out? Well, the answer is because the coefficients may be different. The samples may be different, and that spreads out the spectrum. But the point of the matter is these things do not overlap. Now, of course, if I were to sample faster, so take my spacing to be smaller than this, well then what happens here is the spacing here in frequency gets larger. These little bumps, these little supports of F, get farther apart, and there's gaps between them. Have I lost any information? No. On the other hand, what if I make it smaller? Then these guys get closer together. I take too low of a sampling frequency. Then they start overlapping. I'm taking linear combinations of them. And I don't necessarily know where one blob begins and one blob ends. I start losing information. And this is why the Shannon-Nyquist sampling theorem works. It's telling me exactly the condition at which these two sets of supports are going to butt up to one another. Okay. Now there's one final bit. So now we've got our data. We went from the analog domain, the F, and turned it into this sampled discrete data. Okay, that's kind of cool. And there's one last little operation that we want to do there. If I'm working with this data, working with this sample function, something of this sort, what is its Fourier transform? Well, it's that. Is there a way to compute that quickly and easily and effectively? So we did this by convolution. But let's see if we can write it down in a sensible fashion. So, Fourier transform of this directly, as opposed to looking at it through this convolution standpoint. So the Fourier transform of this sample thing is what? Well, let's see. X. Notice the only x dependence is right here. E to the minus 2 pi I x dx. Again, I want to switch the order of sum and integral. No problem there. I can do that. At least I'm saying I can do that. I can formally do that. Right? Okay. And let's see, there's this f n over 2b. That doesn't depend on x at all, so that's a constant. Take that out. Okay? And what is this? This is delta n over 2b. E to the minus 2n pi I omega x dx. We just saw this integral just a moment ago, but now with these different coefficients. this is now e to the minus 2, what was the value here? 2 pi I omega, the x is now n over 2b. That's it.